now.
Going live now.
We are now live and recording.
Great. All right. Well, welcome everyone. Apologies for the technical difficulties and expecting people to kind of trickle into this new crowdcast room. But you're in the Xarray tutorial, and we are going to get started in just a minute. On my screen, you're going to see a binder session running Jupyter Lab and a few Jupyter notebooks open here. This is what you should have on your screen. I'm going to continue to drop the link to the binder URL here in the chat. So that's where you should be going. And we're going to start in about 2 minutes, I think. Unless Alex tells me we should wait longer. Just going to make sure everybody's here. What was that, Alex?
2 minutes is good.
2 minutes is good.
I said okay. 2 minutes is good.
All right, so we'll start just after 7:15, 7, 8, 9, wherever you are.
Some hour,
quarter past the hour. And you should be opening up the binder link in the chat.
Is it easy for you to move the Dask
yeah. I've reloaded the screen
to the left? To the left. So right now what is happening is that your photos are hovering over the text.
Yeah.
So if you could move them to the right of the screen, that would work nicely. Because you could keep awesome.
Something like that. That's what you're going.
Perfect.
Cool. All right. Great. Just another minute. Any questions? Oh, just see a question pop up here.
Do you want to answer it? The question about whether...
Yep, I can answer it here.
What? Right.
Oops.
So you're able to answer the questions, Joe?
I'm able to comment on the questions. But
the answering,
answer.
So if you want to answer them orally, you can tell me and I can click the start answering, and then they'll record a timestamp with what you're saying. In addition to, if you want to type in a link, it's much better to type the link as a comment. But if you want to, instead of typing the answer, if you want to say it out loud, we can do that.
Yeah. Okay. So a few people are getting failed to connect to the event stream on Binder. Go ahead and just refresh your page a couple times if that happens. That's probably a network thing on somewhere between your browser and Binder. I went ahead and zoomed in a little bit on the text. Hopefully this is better. All right. Well, I'm going to go ahead and get us started on some logistics and some introductory material, and then we're going to jump into the tutorial material after that. So I want to welcome everyone and to the Xarray tutorial, and I want to introduce the three of us that will be doing the instruction today, and then we also have Stefan Hoyer, the original author of Xarray, in the chat, who will be kind of helping answer questions and that sort of thing. So he'll be roaming around. The three of us are, my name's Joe Hamman. I'm a scientist at the National Center for Atmospheric Research, and I also work at a nonprofit called Carbon Plan. Ryan Abernathey is here. He's a professor at Columbia University in oceanography. And then Deepak Cherian is also a scientist at the National Center for Atmospheric Research, and also an oceanographer. So those are the three of us you'll be hearing from, and I'll let them introduce themselves when they do their original or their first presentation slot. I'm going to now close this little untitled. This was just telling you a little bit of what I had been talking about. And let me just pull this all the way up here. Give me just a sec. Oops. There we go. Okay, so we're going to start in the notebook 00 overview.ipy and b. So this is the overview notebook. There's not any code here to be run, but I just want to talk through some of the logistics on the tutorial. And Ryan, please interject if there's serious questions that require me to slow down and adjust things. So, Xarray. Today we're going to be talking about Xarray, which is an open source Python package for working with multidimensional labeled data sets. We're going to be talking about a related ecosystem of tools from Pandas to Dask, Numpy, and some data storage formats like NetCDF. So those are going to be terms we cover over and over again as we go through the tutorial. The tutorial setup, hopefully you've already done this, but there's a link to the binder. The binder URL is in the setup instructions in the repository. You should have already seen that. It is possible for those of you that are interested, or maybe you want to revisit this material later and not run it on binder, to install all of these dependencies locally. And these are the steps to do that. For today, I really encourage you to just use binder. I think it'll be a smoother experience for you. It's also possible for you to mostly just follow along today with the live stream if you don't want to be doing the hands-on coding. We have a few useful links in this notebook. There is documentation for Xarray. So that looks like this. You might want to keep this open in a separate tab. And this is where the API references and a lot of examples and tutorial material. It's also the Xarray code repository. So this is at pydata.xarray on GitHub. This is where we do all of the Xarray development, and also where you might go to file any bug reports or issues, feature requests that you might have. We also have an active Python Xarray tag on Stack Overflow. So after today, if you have questions, that's a great place to ask, how do I do X, Y, or Z? Stack Overflow is the place to do that. So onto the tutorial structure. The tutorial is made up of a bunch of Jupyter notebooks. We're going to go through those Jupyter notebooks in sequence. If you haven't used Jupyter Lab before, you're looking at the Jupyter Lab interface right now. Jupyter notebooks have a mix of code and text, visualization, and exercises that we've mixed in. And we're going to get to experience all of those elements today. There are two kind of command modes. There's the command mode. Sorry, there's two modes: the command mode and the edit mode. You can enter the command mode by pressing enter, and you can execute a cell by pressing shift enter or hitting the play button up here in the top corner. The layout of the tutorial is shown here in this numbered list. We're going to do the introduction and introduction to Xarray and data structures first. Then we're going to talk about how to work with labeled data in Xarray. We'll move on to doing computation with Xarray, plotting and visualization. And then we're going to end the day with a focus on using Xarray with Dask. And Dask is a library for parallel computing and allows Xarray to do scalable data analysis in a really exciting way. So scattered into the notebooks, we're going to see things like we'll see certain exercises. These are opportunities for us to, for you to write some code yourself. And you might see various places with a comment in the code that says your code here. So in this case, there's a prompt above that says print the text hello world. So I'm going to say print hello world, exclamation mark, and I'll run that by pressing Shift Enter, and I'm not connected. That is perfect. Let's see if I can reconnect to the kernel here. It looks like I just did. Okay. Terrifying things happening today. So I went ahead and I typed print hello world, and I executed the cell, and you'll notice that there was a little ellipsis here. This is the solution, and I went ahead and expanded that solution, and I can see that that I got the right answer. So not all of our exercises have explicit answers and solutions built in, but you'll notice when they do. It's important in some cases to actually do the solution for the rest of the notebook to continue on. We're not going to go through these going deeper materials here, but we wanted to leave a list of kind of high quality notebooks that use Xarray in some interesting ways as a way to show some real world examples that you might want to go look at after we're done today. So I have 4 notebooks that I've listed here, 2 around Xarray, using Xarray with weather and climate data. So the first one is looking at global surface temperature in a climate model archive. The second one is looking at the national water model stream flow and using Xarray to do data analysis on that data set. Those 2 data sets are pretty different in their format, and so it's an interesting comparison. If you're interested in Landsat 8 satellite data, the Landsat 8 notebook is really nice, and it calculates NDVI using Xarray and Dask. And so those are 2 geoscience examples. There's also Xarray and is used in a number of Bayesian statistical modeling packages, and so this is an example of using Xarray with PyMC3. All right, so that's the main logistics and overview of the tutorial. I'm going to take a couple-minute break, and we're going to switch over to the data structures piece. I want to ask Ryan how we're doing on questions, and if there's anything major that we need to focus on. You're muted, Ryan.
We are good, Joe. Mostly just trying to help people get connected to Binder who are having problems with that. But I think many people are connected, so I would carry on.
All right, great. Well, I'm going to have a sip of coffee and switch over to the data structures notebook here and make sure I have a kernel. Just take a minute to take a deep breath, and we'll be getting going. Okay, let's go ahead and get going. So this next section is the data structures for multidimensional data, and we're also going to cover some of Xarray's input and output functionality. So at the beginning of each of these notebooks, we're going to have a little section here that lays out our learning goals. So the 3 main learning goals for this part of the tutorial are to understand the basic data structures of Xarray. You should, by the end of this, know how to build and inspect both data array and dataset objects. And you should have a pretty firm understanding of how to read and write various data formats like NetCDF and Xarray using Xarray. Scroll down a little bit here. So as an introduction, Xarray is really designed to work with multidimensional or n-dimensional. We'll also refer to this as ND arrays. Some people refer to those as tensors. And we know that these are really an essential part of computational science, and they're ubiquitous across many scientific domains. We know that Xarray is, for example, widely used in the geosciences. It's also used in physics and astronomy, bioinformatics. We've seen it used in a bunch of different applications. In Python, NumPy provides the kind of fundamental data structures for multidimensional arrays. And what Xarray does is adds a set of metadata conventions and utilities to describe the labels of those multidimensional arrays. So as an example, I have a data set here that's shown with in this figure that has two data variables. We'll call those temperature and precipitation. So this is a weather forecast. And it has two coordinate variables, latitude and longitude. Those latitude and longitude variables are two-dimensional, and the data variables are three-dimensional. The dimensions also have names. In this case, it's X, Y, and T. And all of these concepts, data variables, coordinates, and named dimensions are all part of Xarray's data structures. So we'll get into those in a bit. So Xarray doesn't just keep track of its labels on arrays. It also uses them as part of its interface to doing computation and introspection. So we might do today you'll learn how to apply operations over specific dimensions. So I might want to take the sum of an array over the time dimension. So this is a similar concept to taking the sum over a numerical axis. In NumPy, you might say, I want to take the sum over axis equals 0. Xarray allows you to be more explicit about what you're doing and say, I actually want to take the sum over the time dimension. Xarray also allows you to select values based on label. So here I'm showing an example of grabbing or indexing by a date string. And there's a couple ways in Xarray to do that. Xarray also uses those labels during mathematical operations. So when we do a vectorized arithmetic like x minus y, the labels are going to come into play as Xarray understands how to use them for broadcasting in arithmetic.
Joe, we're getting a request from folks to just expand your Dask sidebar a little bit so that our video is not covering up. I think that should be good. That's better. Yeah, that's definitely better. Great.
Okay, great. Thank you for interrupting. That was perfect. Okay, so Xarray also does group by. So much like the Pandas API for group by, we can do something like group by, and here I'll group by the day of year in the time coordinate, and then I'll take the mean. So that looks similar to a Pandas API and has some additional functionality because we have named axes. And then it does coordinate-based alignment. So this is similar to what you might find in a database where I'll align X and Y and I'll join on their outer coordinates. So finally, we can keep track of arbitrary metadata in this attrs object, and we'll see that later on in this notebook. From here, I want to jump into the data structures part of Xarray, and I want to talk about two specific data structures today. I'm going to talk about the data array. You can think of data arrays as a single variable, and a data set, which is a collection of those variables. So the first one is going to be data array, and I'm going to just scroll slowly so as not to make you sick. So the data array class is used to attach a name, dimension names, labels, and attributes to a single array. So here we're going to create an example array, and I have found myself a typo, so I will fix this really quick. But we're going to create an example array named DA, and we're going to use three-dimension names X, Y, and Z. so you can go ahead and run this first cell. So I hit Shift Enter. If you remember, you can also hit the play button. We're going to import Xarray and Numpy, and then we're going to set the random seed. We're going to use the random module in Xarray, and I want everybody to have repeatable results from that. In this case, we're just going to use NumPy's ones function. Okay, so we're going to start by creating the data array. The first thing we do is create a NumPy array of ones. And then we're going to assign the dimension names, X, Y, and Z. We're going to tell the data array object that we want its name to be A. So I actually was not, there wasn't a typo above. I got ahead of myself. And then we'll assign some coordinates, Z and U, Z being a coordinate array along the Z dimension, and U being a coordinate array along the X dimension. This will make more sense as we go through how coordinates can be assigned to dimensions that don't have their same name. And then we're going to have some arbitrary metadata. In this case, we'll just say a key value pair of adder and value. This can be anything you want. Okay, so we just created this data array, and we are finding a couple little typos. So we're going to fix that. So it's a 3x4x2 array, and all the values are going to be 1 in there. There's some simpler constructions of data arrays when you don't have multiple dimensions. This is an example of creating a one-dimensional data array. So we covered this. Chords is a dict-like object, and adders is a dict-like object. And what we're going to move on to now is looking at some of the string representations, learning how to introspect these objects. So the first thing we're going to do here is just display. Display is a Jupyter function. It's similar to print, and so we're going to print the string or the text representation, and I'm going to scroll so I can see as much of this as I can. Okay, so that's the whole output. So what we see here is we have a data array. It's named A. It has 3 dimensions and their sizes. So X is 3, Y is 4, and Z is 2. We have we can see a snapshot of the NumPy array, and that's printed here. And then down below, we have coordinates Z and U. You notice the asterisk here is referring to Z as a dimension coordinate. A dimension coordinate is a coordinate that shares a name of a dimension, and they get some special handling at times. They have some kind of special powers in Xarray, as we'll see as we go along. There are also 2 dimensions without any coordinates. So X and Y, we didn't assign coordinates with those names. So Xarray tells us that we didn't have it coordinates there. And then we have this arbitrary attribute adder value. Okay. So there's another way we can look at I should just note really quick, this text is what I just walked you through, and I'm not going to read it as I go through. There's another way we can look at these objects. We can look at the HTML version. So this is an HTML representation of the same information we just showed in as text. So here we have and we're going to mostly use this representation today as we look through things. I can click on the little data icon here and get a look at the NumPy array. When we get to Dask later on, this is going to show the contents of the Dask array instead of the NumPy array. But this will always kind of be the closest view you have to the data itself. Here are the coordinates. So we have Z and U. We can click on the data to see their values. And if we had attributes associated with them, some metadata, we could click on the sheet icon. And all of these things are interactive, and we can configure them as we like. So we've gone ahead and looked at the string representation and the text representation. Now we're going to look at inside the actual attributes on the data array. So the first one is data. So this is where the actual NumPy array was assigned. And in fact, da.data will always either give me an array of either NumPy type or Dask type or some array type. da.dims is going to return a tuple of the dimension names. And da.chords is going to return a chords object that has, in this case, Z and U. And of course, da.adders is just a dictionary of attributes that we assigned when we created the object. So a bit more on the coordinates. So I mentioned that chords is a dict-like mapping of names to values, and they are another data array. So this is where we are assigning labels to the data array, and in fact, those chords are data arrays themselves. There's a short form. You can create these as a tuple where you list the dimensions, the data, and the attributes in the tuple form, or you can create a full data array using the full syntax. You can also use just a NumPy array, and Xarray will, in many cases, be able to create the coordinate for you. So here's an example of 3 different ways to do that. Here, I'm going to create a new data array of shape 3 by 4. It's just going to have 2 dimensions, X and Y, and it'll have 3 coordinates. X is going to be a dimension coordinate. I don't need to specify its dimension because X is already a dimension. And I am just going to use string values A, B, and C. Y is also a dimension, so I don't need to specify its name, and I'll just use a NumPy array. In this case, I'll just use 1, 2, 3, and 4 using NumPy A range. And then U is not already a dimension, so I need to assign a dimension to it, and I'll use the tuple syntax here. I'll go ahead and run that, and we'll see that it created a new data array with 3 different coordinates. Okay. So we are going to be able to use I mentioned just briefly that there is the notion of dimension coordinates, and I just want to highlight, and we're going to get into this as we go into more of the details on indexing, that certain things only work with dimension coordinates. Some indexing operations are not going to work with the U coordinate in this case. That's Go ahead.
There's a question right now that has 6 votes, which is, can you explain in more detail what is the difference between coordinate and dimension? You just addressed that a little bit, but maybe say a little bit more.
Yeah, okay. So this is a really good example. So a dimension is a map. The dimensions are a mapping of the array shape to the name of those of each dimension. So in our case here, I have a dimension X, and its length is 3, and a dimension Y, and its length is 4. Whereas coordinates are the labels along that dimension. So X in this case has also a coordinate which is A, B, and C, but that's different than the dimension length. Hopefully that straightens things out. So we're going to take a pause here, and we're going to do an exercise. We want to take a moment to create a data array named height from some random data. We went ahead and created the NumPy array for you. So here we have a NumPy array of shape 180 by 360. And what we want to do is create a data array with dimensions, latitude, and longitude. So I want everybody to get a shot at that. I'm going to be quiet for about a minute, and then I'm going to actually start working on this myself. Okay. So I'm going to go ahead and work through this. Hopefully you've had a chance to do this yourself. So we're going to do height. Oops, sorry. All right, so I can leave this one as is, and we can take a look at the data array. And then there's a second exercise right below, which is to add the coordinates with specific step sizes. So I'm going to go ahead and copy my results here, and then I'm going to add a chords object on this next section. I'm going to let you get a head start on that, and then we'll go from there. Oops. Okay. And I have a syntax error. Missing a comma. So what I've done here is I've added two linearly spaced coordinate variables with using numpy.linspace, and I created a dictionary of those that I gave to Chords. And you can see that I now have two coordinates, one for latitude, one for longitude, and that the spacing is 1 degree. I am off by 1 on my Chords, but that's fine for here. Okay, and finally, we're going to do the same thing, and we're just going to quickly add some metadata in the adders object. So this is adders equals, and you can put in whatever you want here. I'm going to say created by, and then I'm going to say Joe at SciPy. Okay. And this will then give us a metadata object with an attributes object with the created by key.
So you're getting asked to slow down.
Okay, that's great. Let me go ahead and pause here, and I'll let we'll give a couple more minutes for people to finish this section, and then we'll do the data set.
And people want to know if the solutions are going to be posted somewhere.
We can post the solution somewhere. We haven't at this point. Yes, Scott, we could have used a range here.
And then Falk asks, what did you mean by height in this exercise? Is it just an annotation?
It's just the name of the NumPy variable. So I'm going to scroll up to show when we created that originally. So in this case, height is just the name of this this random array, but we could have assigned the name of this array to height, which then would have given us the label height on all of our arrays.
And then people also want to know, maybe this would be a good, oh yeah, okay, you just added the name to the data array, right? That was what I was going to ask. So apparently the binder team has just bumped up our capacity, and we should be all good, and we owe them big time.
We totally do. Thanks, Carol, for being here, and we'll be sending treats. All right. Ryan, do you think we can talk about the data set now?
Yeah, let's move on.
Okay, great. So the next section in this notebook is going to be looking at the data set object in Xarray. So a data set is a collection of one or more variables, and you can think of it like a dict-like container of data arrays. The constructor has three main parameters. We have the data vars parameter, which is going to be a collection of data arrays. The chords parameter, which is going to look quite similar to what we just used the chords object for on the data array. And then the adders, which again is going to look like an arbitrary mapping of metadata. So let's go ahead and create a data set with two variables. The first one we're going to create is shown here. We're going to create a data set with two data vars, A and B. A is going to have two dimensions, X and Y, and it's going to be of an array of 3 by 4 and of just NumPy ones. Okay, and then a second variable B, which will be one-dimensional along the T dimension, and we're just going to create a full array of length 8 and fill it with 3. And we'll go ahead and pass in the adder value here as the attributes. We're going to give this a single coordinate variable X, and we'll just have -1, 0, and 1, and then some global metadata. Go ahead and take a look at what that looks like. Now we're going to, again, walk through both the string representation and the HTML representation of this array and try to learn a little bit about how the data set is laid out. I'm going to... For just a second, I'm going to zoom out so this whole thing fits on one line, but I'll zoom back in a moment. Here we have an Xarray data set with 3 dimensions, T, X, and Y, and then we see their dimension length. We have one coordinate variable, X, and this is a dimension coordinate, and we see the asterisk here again. It has 3 integer values. We have 2 dimensions without coordinates, T and Y. And we also have 2 data variables, A and B, and we can see there the dimensions that are associated with each of those. As we'll see later on, these data variables can share dimensions and they can share coordinates as well along those dimensions. Finally, we have this global metadata attribute and value. I'm going to zoom back in before I forget. Go ahead and look at the HTML representation. So here we see all the same things. We see the dimensions, T, X, and Y. In this case, the dimension X is bolded because it has a coordinate associated with it. Then we have two data variables, A and B. Remember, we added some metadata to B, and so now I can toggle this, the metadata tab here. I can also look at the values in each of these. So that's how the HTML wrapper works. I may want to add some coordinates to my data set. And so what I'm going to do here is I'm going to start with creating two data vars, A and B. These are going to have each two dimensions, one X and Y and one T and X. So now we're going to have a shared dimension between these two. And then we're going to have three coordinates, one for each of the dimensions above. And I'm going to create these in three different ways. I have a list of strings. I have an array of integers or floats. And I have an array of pandas datetime objects. I'm going to go ahead and create that, and we're going to look at what this looks like. So now I have a new HTML wrapper to look at. T, X, and Y are still here. We can now see all their coordinates, and we can note that we have a new data type here, the datetime 64. So this is an array of datetime objects. We can take a look at those. And then we have two data variables, A and B. These two data variables, again, are data arrays. Next, I'm gonna just highlight that there are some shortcut syntaxes for creating data sets when you have data arrays already. So here I'm going to create two data arrays, A and B. And I'm going to do that using Numpy arrays and then adding some dimensions and coordinates to them. And when because those two data arrays have coordinates associated with them, I was able to just pass in only a dictionary of data vars to the dataset constructor, and it managed to do the merging of those two X coordinates on the fly. And you'll notice it inserted some nans or some missing values in places where the coordinate values for A and B didn't overlap. And so that's what happened here. Xarray uses nans as its missing value almost exclusively, and so we're going to see this nan show up quite regularly as we go through the tutorial today. Next, we're going to do an exercise. We're going to create a data set with two variables, latitude and longitude. Two variables along latitude and longitude. Those are going to be height and gravity anomaly. And I'm going to give everyone a chance to do that. We went ahead and created the data, the Numpy arrays for you. And the task right now is to create the data set with those. So I'll just give you a minute to do that.
So question from Antonio, how did it join the two data variables A and B? Did Xarray realize X dimension as the key, or was it the X coordinate? So
yeah, it was a bit of both. And did Stefan just answer, or should I talk about it?
You can answer.
Okay, great. Yeah, so it was a bit of both. Along the X dimension, both arrays shared a common coordinate, which was X. And so it was the coordinate itself that was used for the alignment there. The broadcasting happens along dimension names, but the label alignment happens on the coordinate.
And if you don't have a coordinate, but you just have dimensions with no coordinate, that it fails unless everything has the same shape, because it's not possible to know how the data arrays align with each other.
All right. Well, I'm going to go ahead and start on this exercise here. So I'm going to add a data vars object. Should be just making sure I'm still connected here. Looks like I am. So I'm going to create a height. Oh, what happened here? And a gravity anomaly. All right. I'm going to remind myself. I'm going to actually do it the slower way, because this is how I would typically do it, and I've just made a mistake on live stream. It's embarrassing. Here we go.
A lot of folks are asking if we can post the solutions. So we'll update the tutorial with the solutions after this is over.
There we go. All right. So now I've gone ahead and created 2 data arrays. And here, why did I delete that?
And folks are asking you to slow down.
Okay. I am going to talk through what I've done here. So following the example above, where we created 2 data arrays from our NumPy arrays and then passed those data arrays to the dataset constructor, I'm going to go ahead and follow that same pattern in the exercise here. So the first thing I'm going to do is create a data array for both the height and gravity anomaly arrays. And so that's what I've done here. And we can go ahead and take a look at those. The height DA is looks like this, and the gravity anomaly would look similar. So we see our latitude and longitude dimensions, and I haven't assigned any coordinates. From there, I can pass a dictionary of data variables to the data vars property. And what I've done here is I've created a height and assigned that to height DA, and a gravity anomaly and assign that to the gravity anomaly DA. I'm going to go ahead and run that. And I'm going to see that, in fact, I created a data set with 2 data variables, both along the latitude and longitude dimensions.
So we haven't asked for a review of the abstraction so far, and a request for a use case besides just latitude and longitude. I don't know if we have time to come up with a different example live, but maybe we can just talk through the basic concepts of dimension, coordinate, data array, data set again.
Yeah, so the dimensions here can be anything. So I'd feel comfortable swapping these out with X and Y, or even time and sample. Okay, and we could do that for both of these. And here we are now looking at a data set where the dimensions are sample and time versus latitude and longitude. These are arbitrary names. The labels of the dimensions and of the coordinates are completely determined by the data set themselves. Xarray doesn't care if you have latitude or longitude. Yeah, I'm gonna just scroll back up to this image that I showed at the beginning, and talk. Sorry, we've added a lot of output, so I'm now scrolling pretty far. To come back to this image where we now have a data set where we're constructing, where we're adding various labels to it. So in our case, we were just we had gravity anomaly and height. Those were these two variables, temperature. Those are the analogs to temperature and precipitation here. And then the latitude and longitude are the dimension names. And so that's the X and Y, or X and Y and T in this example. Depending on the type of data you use, those things are all going to change. And so I can swap out X and Y for sample and time. And I can swap out temperature and precipitation for any variable name you have. All right. I'm going to go ahead and scroll back down to where we were last. So we have a couple more pieces of the exercise here to do. I'm going to go ahead now and add, revisit our example from above. We're going to now add coordinates to our sample arrays here, height and gravity anomaly. And just like we did for data arrays, we're going to do the same here for our data set.
So a lot of folks, I think, are kind of getting confused about this because we haven't shown what you can do with these coordinates yet, right? So, soon later on in the tutorial, we are going to use these coordinates to select data and to plot data. So right now we're just creating a bunch of arrays, and it does feel a little bit like busy work. But for when we put them to work, I think it'll make a lot more sense why we have these data structures.
Yep, that's a good point. Okay, so I'm giving folks a minute to do the second part of this exercise where we add coordinates. And I'll just remind folks how this can be done. We can add a dictionary of coordinates along those dimensions in multiple ways. So I'll just leave this here for a second. All right, so what I'm doing now is I'm adding coordinates along coordinate values. I mean, this time I'm using a range. Oops, and that should be 2. Okay, and so I've added a coordinates object with the keys as strings that match the dimension names and values as NumPy arrays. All right. So this is very similar to what we did before. And when we were just working with the data array, we just added a Chords object. Now I've added that Chords object directly onto the data set. Finally, last piece of this exercise section is we're going to add some metadata to this object. So I'm going to just walk us through that by first adding starting with where we just left off, and going to add a few pieces of metadata in a few places. So let me grab the whole section from up here. So we're going to add some attributes to the height array. Here I'm going to add do some copy and pasting so as not to introduce typos. Ellipsoid, which will be WGS84. So this is some domain specific metadata that I wanted to add. For the gravity anomaly, I'm going to do something similar. All right, and now I'm going to add some metadata to the latitude and longitude here. And I'm actually going to refresh my memory on the short notation for creating these. Where'd it go? All right, so this is the short notation where I can specify a dimension, an array, and then attributes. Okay, so I'll just copy this down so people can see the shorthand notation. In this case, I'm going to say latitude, the array, and my attributes, which for latitude will be here. Okay, and I'll do the same for longitude. And I just want to underscore that there is the actual metadata I'm adding here is very specific to the domain example that we're using, but is something that, depending on your area of research or your application, you would be familiar with the type of metadata you would want to add here. So I went ahead and created this data set, and we'll take a look at what that looks like. So we have dimensions, latitude and longitude. We have two coordinates now, latitude and longitude. They're each along their own dimension, and they have some metadata associated with them, which I can expand. I can also look at the data in those arrays. I can...
Joe, we basically lost a lot of people. We're going way too fast. So I think we're going to need to change up our pace a little bit.
Great. That's good feedback.
I think folks are having a hard time because the screen is very small and we're doing a lot of scrolling. And so it's really easy to get lost and not know really where we're at right now in the tutorial.
Okay. So we're right at the bottom of the data set section, right before round tripping and IO. And I want to encourage people to kind of be okay with not understanding all of the data set constructor logic here. A lot of times when we create data sets, we'll be loading them from an existing data set, which is what we're going to talk about next. So what we wanted to make sure you were familiar with here was the differences between data arrays, which are single kind of variable objects, and data sets, which are collection of variables. And that you have some idea that we have the notion of dimensions, coordinates, and and attributes. So if you've taken that much from this part of the tutorial, you've picked up 90% of what we wanted you to get, and that will be perfectly sufficient for you to follow the rest of the tutorial today.
Which we will slow down and do at a slower pace from now on.
Yep. And I think
you're being asked to scroll up and show your last cell again.
I'm reformatting this so it all fits on the same line here. So here, I'm just going to walk through what I've done here. So this is the same notation we used earlier when creating data arrays, but I'm just going to talk through how I created the chords with their attributes. So the shorthand notation for how to create a data array is by passing a tuple of the dimension, the data value, the coordinate values themselves. So in this case, it's an array, a Numpy array, and the any metadata. So this is a dictionary of this, in this case, of with a single key, type, or ellipsoid.
Coordinates are their own data arrays. Yep. Coordinates are just other data arrays. So I think there's some questions about some people are confused that coordinates and dimensions can have the same name, and that's actually really important. So when a coordinate does have the same name as a dimension, that's called a dimension coordinate, and that's something really special in Xarray. That basically tells Xarray to create an index out of that coordinate, and that can be used for looking up data. So rather than being a conflict in names, actually, it's really important that if you want to use all of Xarray's indexing and plotting capabilities, that you do create coordinates that have the same name as your dimensions. You can leave those coordinates out and just have labeled dimensions, but that's not nearly as powerful as if you have actual data coordinates associated with those dimensions.
There's a question here about attributes. So attributes are arbitrary metadata. They can be of multiple types, but they all have a string key and some value. There are auxiliary metadata associated with either the data set or individual data arrays.
And we have a request for a break.
Great. Should we take a break right now then, Ryan? Or, after we finish this?
We need a break now, yeah.
Okay, great. We'll hang here. We'll continue to answer questions. We're going to take a pause here, and we'll pick up with some the next section of the tutorial in, we're going to take 5 minutes, Ryan, 10 minutes?
Let's do 10 minutes.
10 minutes. Okay, so at 25 past the hour, we'll be back and starting again. Everyone go get some coffee.
I'm going to propose we skip the IO and round tripping.
I'm all about it.
People can read up on that. And I think moving to indexing next will just answer a lot of the questions that people have.
I totally agree. I was going to suggest the same thing. So, yeah. It does sound like there's some questions and some confusion on the shorthand notation for how to create these coordinate data arrays. And so while we wait here, I'm going to rewrite just this one line in a way that might help answer some of that. Oops.
And we're asking people want to resend the binder link. I'll try and find that.
So,
people just want to see a tiny bit more of the last cell.
Of this cell?
Yeah.
Great. So Chuan asked a question about Xarray. So we're gonna skip Xarray for now. We'll have opportunities to see pieces of it later. But the answer is whether or not the question is whether or not when you are using Xarray's Xarray reader, if it automatically uses Dask by default, and the answer is yes. And you can turn that off if you want to. So Marcel asked whether or not data arrays and datasets and chords can all have arbitrary adders, and the answer is yes. Deepak, are you, or maybe Alex, maybe you can sub in Deepak as Ryan's backup for this next section, and yes. I'll answer questions in the chat.
Okay, should I kick you out now?
You can kick me out now, Ryan. Are you ready to take the screen share?
Give me 1 minute to close all of my tabs.
Yeah. No worries.
Okay.
Great. Deepak's here. And
I am ready.
There you go.
Okay. Bye, Joe.
All right. Ciao.
Okay. Now I should share.
Yes.
Okay, so I'm going to make this a lot bigger. I'm going to take a different approach here. We're not starting yet. What's our official start time? Can someone?
Another 3 minutes or so.
Okay.
What we can do also is if we all turn our cameras off, we won't our faces won't overlay with the shared screen. The shared screen will take all the space.
That sounds like a good idea.
Okay. Then I
Cameras off.
can turn your camera off from here. There we go.
All right. I'm here. And
Right. I guess the audience can't really talk.
Yeah, and Alex is muted. Oh, he's here.
I'm here. I'm here, but I didn't go anywhere, so I'm not the target audience. So you should wait for a few thumbs up
People
and
seem good to
yeses.
go. Okay, so welcome back, everyone. My name's Ryan, and in response to the very helpful feedback we got, we're going to really try and slow this tutorial down. Remember, Deepak, that I can't see the questions in the chat, so you have to interrupt me and say something if you need me to stop or change anything, okay? I just see my own screen. So
I'll jump in.
in order to slow things down, we're not going to be working, I'm not going to work from the executed or pre-filled notebooks. I'm going to type all the code live. And this is what I tend to do in all my teaching, and it works well because it allows me to not go too fast. So what we're going to do now is we're going to work on the second notebook, working with labeled data, but I'm basically just going to type the code in live and tell you what I'm doing as I do it. Okay. And so hopefully this will keep the pace slow. If you want to know what I'm going to do ahead of time, you can switch over to that notebook, which I guess we can also put on, I'll put in the chat real quickly. Let's see. I will put this quickly in the chat. And this notebook is not going to be saved and shared on GitHub because I'm just going to type in what we already have in the notebook. So hopefully there won't be anything new or different there. Okay. Let's import Numpy, Pandas, and Xarray. And I'm going to set my random seed so that we are all going to get the same results. If you want to get the same thing as me, you can run that. And you're going to see I'm going to make a lot of mistakes and have a lot of typos, but I will fix them all live. So let's talk about first how we do indexing in NumPy. So let's create a NumPy array, a random array of shape 3, 4. Here's an array of 12 values, 2-dimensional array. Now we can index that array based on position. So this is going to get me some slices. Sorry, I meant to do this like this. This is going to get me a little slice of that array. Up to the second index on the first dimension and starting from the first position on the second dimension, second axis. We're assuming that since this is an intermediate tutorial, everyone here has done that kind of indexing with NumPy arrays before. So now we're going to show you how we can get data out of our Xarray data arrays. Okay, so what we can do here is now I'm going to quickly create an Xarray data array. So using the sort of syntax we learned last time, I'm going to put this NumPy array into an Xarray data set. I'm going to call these dimensions X and Y. Dims. Okay? So now I have an Xarray data array that has that NumPy array in it. And what I can do now is rather than having to remember, which dimension, which axis corresponds to which dimension, I can just get data based on position, based on those dimension names. So I could say, for example, Xarray, I can do R, I cell. So the way we can do index-based selection in Xarray is using this method called iCell. I'm going to say I want the first position in X and the third in Y. So what this did is it just got those positions out of the array at the locations I wanted. And an alternative way to do the same thing would be to use a dictionary. You can say x1, y1. So this is useful because we can select data based on its position, based on a named dimension rather than just axis 0 or axis 1. Now, we can also do the same thing on data sets. So I'm going to quickly create a data set. So I'll say ds equals xr data set. And I will fill this in and I'll say I'll have one data variable. So those of you who had questions about syntax, about this for creating data arrays, here's what it looks like.
Ryan, we have a request to scroll up a little bit.
Okay, sure.
Thanks.
So what I'm doing now is just creating another data set, a data set with two data variables with the same dimension. So this is using that dictionary syntax to construct a data set. And I can do selection across both of these data variables in the data set at the same time. So I could do, for example, ds icel x equals 1, y equals 1. And that gives the values of both of those arrays at that position. Now, in my original example, I used the slice. So I can always fall back on standard NumPy slicing notation. So I can access one of these data variables, A, and I can say, like I did before, I can index the array using, the standard get item syntax from that we use in NumPy. So I can use the square bracket operator and put in the positions I want. If I want to do the exact same thing using icel, we need a different way to pass that sort of so-called slice. So the equivalent, the exact same thing as cell 13 here is if I write the following: slice none 2, y equals slice 1 none. So this slice operator is a way, and I'll just put one of these on its own line. This slice is a built-in Python language primitive for these type of indexing operations. So we can accomplish the same thing, selecting a range of data by calling icel together with slice. Okay, so what we just saw is how we can use this indexing to select data from data arrays based on named dimensions rather than just axis positions. I'm just going to take a little break right here and switch over to the chat and make sure there's no crisis going on there. Looks good.
There's an interesting conceptual question here. They're asking, basically, how do you index with a unindexed dimension? So in this case, x and y have no coordinates associated with them. So how are you indexing along it?
Yeah. So it's just using the positions, just the same way NumPy does. So there are no coordinates yet in this data array, right? Coordinates is empty. But that is a good segue to the next topic, which is we want to do, this of course is not really far beyond what NumPy already can do. Okay, it's convenient to use, specify the name of a dimension rather than just saying axis 0. But this really comes into its own once we create some data that actually has coordinates. So let's do that right now. So I'm going to make a new data array. And this one is going to have actual coordinates. So first I'm going to specify the data, np random rand. I'll make this one a little bigger, 4 by 6 array. I'll call the dims the same, X and Y. And now Chords is going to be a little bit more complex data structure. I'm going to specify coordinates for X and Y. So X, I'm going to say, I'm just going to put in some values here, minus 3.2, 2.1, and this could be a NumPy array as well, 5.3, 6.5. And for Y, I'm going to put in, this is why we imported pandas, I'm going to put it in a date range. Date range, I'm going to put here 2009, 01, 05. I do not know why we picked this date. Maybe it's important to Justice, who wrote this example. Periods equals 6. Frequency equals monthly. So this is going to give us 6 monthly values. This is just straight out of pandas. So I'll pause here and let everyone catch up with this array creation, because this is a really important step. So now we've created a data array that has coordinates associated with its dimensions. By the way, if you're feeling confused and frustrated about creating all these data arrays and data sets manually, don't worry. 99% of the time when I'm working with Xarray, I'm actually loading data from files, right? So creating synthetic data like this is something we do only in tutorials and examples and teaching generally. For most real world use cases, which we will get to in the next lecture, you're just going to be loading data from files, and you won't have to remember this complex syntax for creating the data arrays. So I'm going to pop over here and make sure we're all on board. Yes. So now that I have that created, I can do the following. I can select data not based on its position, like the third element on axis 0, but I can write code like this. R cell, the magic method here is cell, X equals 5.3, Y equals 2009, 04, 30. I was now able to pull data out of the data array just based on these coordinates. So, X presumably represents some kind of position, right? So I want the value at position 5.3, and Y is a date. So I want a value on a specific date. So that is one of the first sort of real magic things that Xarray does for us as data scientists, is that it allows us to think at a little bit higher level about our data, and and select data based on its actual natural physical coordinates rather than just some position inside an array. If you're saying this looks similar to pandas, you're absolutely right. This is using pandas under the hood. So in order to do this, there is a pandas index created for each dimension of the array. But the key difference between Xarray and pandas is that you can only have one index in pandas, or maybe a multi-index. But in Xarray, you can have as many indexes as you have dimensions. So something was worth pointing out here. What if I change this 5.3 to 5.4? I'm going to get an error. It's going to tell me key error. We don't have a value named 5.4. Now, an easy way to get around that is you can just add in here method equals nearest, which will do exactly what it sounds like. Okay. We can also select multiple values. So we can do R cell X equals minus 3.2, 6.5, Y, and then we can use slices in data space, in coordinate space. So if I want everything between the dates 2009, 02, 28, and 2009, 05, 31, I can get a range and I can get specific values using that syntax.
Brian, we have a question on method equals nearest. It's how is method equals nearest calculated? Is it based on all the other dimensions and coordinates?
No, method. So each index, there's no notion of distance in multi-dimensional space. It's just used along each axis to map to the nearest indexed value. Hope that answers your question. Okay.
And now a question from Brian. Is it required that coordinate values are monotonically increasing?
No, it is not. Slicing and things like that might always not work as it might not always work as expected, but just like Pandas supports multiple this is, if you know Pandas, under the hood, this is using Pandas, and Pandas allows you to have non-monotonic and indexes and repeated indexes, and so repeated values in your indexes. So all of those are allowed in dimension coordinates. And just to connect to the earlier discussion, this is all possible. Cell is all possible because we have a coordinate with the same name as a dimension. So here's the dimension X and here's the coordinate. So the fact that we have dimension coordinates unlocks the ability to use cell. And if we didn't have those coordinates, we would have to use iCell. And we wouldn't be doing that much more than what NumPy already allows us to do. Okay, and then one final method I want to show you and then move on is that we can also do selecting, sort of the inverse of selecting, which is we can do R drop cell, and I'll put X equals minus 3.2, 5.3, and that's going to drop. So it's like the mirror image. It's going to drop everything that matches those that index and keep everything else. Okay, so question about the difference between loc and iloc, that's a good one. Someone should answer that in the ask a question. We
have questions about assignment. I think you're going to get to that soon, right?
I don't think we have assignment in this notebook.
Okay, I'll answer those. Yeah.
Okay, so let's get onto an exercise because it's going to give us some real data, which is going to be really great. Let's now load our tutorial data set. So in order to do this, we're going to do XR tutorial open data set, and this is just called air_temperature. Okay, so I encourage everyone to load this data set, and our and just have a look at it, look at it. So this is real data now. And what we want to do is the first exercise is select the first 30 entries of latitude and 20th to 40th entries of longitude. Okay, so that's your first exercise. And just to clarify what we mean here by entries, we mean select the data based on its position in the array. Okay, not based on its coordinates. So that should give you a clue about which of the two methods to use. We learned two methods for selecting, iCell and cell. So here we want to select based on entries or position within the array, not based on coordinates. So should you use cell or should you use iCell? So take some time and try and do that exercise. So while you're all working on that, I'm going to start doing it myself. So I'm going to say, okay, first entries of latitude. So DS. Now we're doing entries. So we probably want iCell because we want it based on position. The name of the latitude dimension is lat. And the first 30, I want a slice. None 30. This might be hard for you if you've not seen the slice syntax before. That's how I solved that one. So one thing I definitely have to get used to when working with Xarray is typing slice a lot. Because just the way our API is, you can't actually use, it would be nice to be able to write something like, somewhere write 30 and, 20 to 40. And we could do that with a single variable. So we actually could do that. We could write ds air, except we don't know which dimension is longitude, right? We don't know, is it the first, second, third? So we could do something like, I guess, this one. I would have to manually look at what the dimensions are. I believe, I want to just do this, get all the times. So this works as well to accomplish the same thing. But the sort of correct answer using the syntax we've shown you is the second thing you see here using iCell. So someone asked why I used iCell if I have dimensions and coordinates that have the same name. And the reason is that I am selecting based on position in the array. I stands for, I guess, index or something like that, or integer selection. And so I'm not actually using the latitude and longitude values. But that's going to be the next question. So the next question is, I will just type it out. It is select all data at 75 north between January 1st, 2013 and October 15th, 2013. Okay, so for this one, we want to use the labels. We want to use the dimension coordinates and use the data in those coordinates to do my selection. So are we going to use iCell here or cell? Okay, so I see people answering in the chat, but just go ahead and try and write the code for yourself to do this. Okay, so we're going to ds.cell, and it's going to be something like lon equals something and time equals something. So fill in those dots. What are you going to put in there? So the fact that we want between two dates, that's a little hint that we probably want to slice for time. So we'll put in we can put a date string in here, 2013 01, and 2013, 10, 15. And for longitude, I'm just going to put 75 in here and see what happens. I don't know if this is going to work. I don't know if there's an exact value of 75 in here. Let's see. Yep, I got a key error. Oh, and by the way, I also want lat, not lon. Okay, so there, putting lat worked. So that is the correct solution to the question. So here we selected the latitude by its coordinate, 75, and a time slice between two dates. And that gave us this following data array, which we could then use for further calculations.
Brian, we're getting questions about the behavior of slice with datetime, and in this case, I guess it's selecting dates on October 15 too. I think this is a pandas feature.
Yeah, so that's a really good question. So when we do slicing in index space, like with Numpy or something like that, then it's inclusive of the left value and exclusive of the right value. But since this is actually using a pandas index, pandas indexes have different behavior, and this slice is actually inclusive of the rightmost value. So when you're doing cell with a slice, it is inclusive of both endpoints. That's a really good question. Okay, so I think we're going to just stop here and not do the rest of this tutorial and just help everyone else get, not do the rest of this notebook and just get everyone caught up. Because I see a lot of questions and a lot of confusion in our chat. So let's just resolve everyone's issues as much as we can, one by one. This is really the main. This is really the main core of the concept. Is that of the concept we're trying to learn is how to select data out of our Xarray arrays.
Brian, can you go over the slice bit again? There's still more questions in the chat.
Yeah. So slice here represents a range. It tells Xarray, give me everything along the time axis between these two values. That's just a little bit of sort of syntax we have to learn when we're working with Xarray.
Molly has a question saying, can you use the range of values for lat with cell, i.e. all latitudes greater than or equal to 75?
How would we do all latitudes greater than or equal to 75?
Yeah.
Yeah. So I'll do that right now in the next cell. I'll just say slice 75 and none is how I would specify to go all the way to the end of the array. So maybe I'll give a little decoder kit for slice notation, since I think this is tripping people up. So if I write, I'm going to write some code here. If I write, maybe I'll see slice notation like this. That is slice none 5. Slice 4 none. Slice none 2. And then the most complicated possible slice involves 3 values. Right, so this is just a different way of using the sort of slice notation that you are already using as a Python programmer probably every day. It's just encoding these things into this slice object. Oh, someone wanted all below. If you want it below 75, I'll just do none to 75.
Oh, I think it depends on how lat is sorted, actually. This is a common issue. Hey, Ryan.
Yeah.
I think latitude is sorted in descending order. That's why the slice is behaving funny.
Yeah, so if we actually look at our latitude values, so let's look at this array. Let's go back. I'm going to scroll up now, so get ready for a little whiplash to where I originally loaded the array up here. And if we look at latitude, yeah, latitude starts from 75 and it goes descending. So it's going to have different behavior depending on the direction the array is going. It's a good question. So, you know, it will start, from, if it's descending, the cell will have a different behavior than if your coordinate is ascending. And that's something you can solve just by inspecting your data. And one piece of advice I often give to people who are new to Xarray is use this information in the Xarray repr, right? So there's a lot of information in here. You can see all of your coordinates. You can see your data. You can see the attributes, if there are attributes. Right, so in debugging stuff, looking at that can be really useful. Okay, so I think we should leave the interpolation and broadcasting stuff for a self-study. I'm going to cover some of broadcasting. I'll just say quickly about interpolation. That you can interpolate along these axes. So rather than just selecting data that exists or doesn't exist, you can select intermediate data using ds-interp. I'll give you a real quick example of that. So if I do ds-interp x equal, or rather say lat equals, say much higher resolution than I actually have, 75.0, 75.1, 75.2, it will interpolate along that axis for me. Just using regular linear interpolation. There's a lot more to interpolation, but given our pace, I think it was we can't cover it right now. So let's hop into another 10-minute break here, and we can use that time to answer any lingering questions and get ready for the next part. So we will start the next part of the tutorial at 12:10. And you're welcome to take a break. If you're on the East Coast, you might be starting lunch, or if you want to hang out here in the chat and chat with us and ask questions, we will be here. Someone asked me to solve question 3. Remove all entries at 260 and 270 degrees. That question is vague because it is. And someone also asked me to scroll up. I'll level with you guys as presenting these tutorials is hard because you have to make the text large, which means you can't have a lot of stuff on the on the screen at one time. So you kind of have to choose between making the text readable or showing a lot of stuff at once. So this is a kind of irresolvable challenge, but I'll do my best. So I'm going to solve question 3 to remove all entries at 260 and 270 longitude. So I'll just add that here. So 3, remove entries at 260 and 270 long. So I will do ds drop cell lon equals, and I'll just put 260 and 270. That is how you solve 3. Okay, so yeah, I'm looking through these questions, and I'm seeing some environment errors and netcdf. NetCDF is a dependency for reading this data, and it's a binary library that has binary dependencies on HDF and stuff like that. It can be a challenge to install sometimes, and that's one reason why we like to use Binder for these type of tutorials, so you don't have to kind of resolve all those dependency challenges. Shastri wants to see the DSL command. So someone asked, Zafar asked a question about Boolean indexing. You wanted to do, you're trying to do select the values of lat less than 75 using a less than operator, creating a Boolean array. And the reason that doesn't work is that we don't really recommend, Boolean indexing with Xarray. Deepak, am I saying that right?
Yeah. This question has actually come up a lot, so maybe it'd be good if you could demonstrate where, with the caveat that it could be.
I don't even like to show people where, because I feel like it encourages the wrong usage. So I don't want to show where, basically. I think it's really important to learn to do Xarray syntactic cell operations using slices, because that is the most performant and efficient way to get the data out of your arrays. So if you wanted to get the latitudes less than 75, I would do what we have here.
So there was a question in the chat where it says, can you select based on the actual value of air? And I think the only solution there is to use var. So maybe that could be an okay example.
Yeah, okay, so we can do that. Well, no, because we're on break now. We're not showing you material. That's not fair to the people who left for the break.
Kelvin Lee has a good comment. He says, think in slices, not in masks. And that is definitely recommended.
Now, at a certain point, you may need masks. And so Xarray fully supports missing data, and you can create masks on these data. All right, I'll show you the dark side if you must see the dark side. So what if I do ds where lat is less than 0? So that's the southern hemisphere. Ds lat. You can do this. What's important here is that this didn't change the size of any of the arrays. You still have all your data. It's just a lot of it has been filled in with nans. Right? So you can mask based on any of the variables by passing a Boolean array to this function where. But that is not efficient because you haven't actually removed any data. So you still have to compute on all those values. Now, someone asks how to plot. We'll just do a little plotting. VS air, ICell, time equals 0. Just to let you know, there's real data under the hood here. First plot. Okay, so you can just call plot on data arrays, and it will generally do something useful. And we will have a whole lecture on plotting if we manage to get that far. So there's a good question about whether you can use bracket notation for cell-like selection if you wanted to set values. So I think that is where we would use loc, right? So there are other selection methods that we haven't gone over, but I think this part of our documentation is pretty good. So if you go read it, you'll see a bunch of different ways, and you'll I think be able to answer that question. Assigning to a slice. I don't know how to do that in Xarray. I avoid that sort of pattern in my workflows, but what do you know about that, Deepak?
I am the same, but I think you can do .loc. I'm trying to pull up the documentation. Let's see. This is why we need Stefan online.
So the reason a lot of us don't do that sort of thing, Felipe, is that we're often using Xarray together with Dask, which we'll get to in the later part of the tutorial. And Dask arrays are immutable. So you can't assign to Dask arrays. And so a lot of us just kind of get in the habit of not assigning to things at all and treating Xarray data arrays and data sets as immutable. It is possible, though. And as Stefan is saying, that has been answered in the answered questions section of the Q&A. Okay, so we're coming up on 10 minutes. My clock just ticked to 12:10. I'm on East Coast time, 11:10 Central time. So we will dive back in. So what we're going to do now is, let me see. We are going to move on to the next example, which is next notebook, which is computation with Xarray. It's notebook 03. It's both on the tutorial website, and you have this notebook for you in your in the binder. But as I did before, I'm going to just type everything live, which I think helps us maintain a better pace. So are we all ready to go? Give me some thumbs up in the chat. Ooh, you guys are leaving me hanging here. All right, thanks, Ming. Oh, I love it. Wow, that's a lot of thumbs. Okay. And I'll just remind those of you who are asking questions in the chat, please ask them via the Q&A. That helps us triage the questions a little bit better. Okay, so I am going to do my imports. I have a fresh notebook, and you can use a fresh notebook, or you can follow along, do whatever works for you, but I'm starting from a blank notebook. Now, I'm going to quickly flip over to the executed notebook. And I'm going to show you what we were originally going to do to load this data. So this is some real data from the National Oceanographic and Atmospheric Administration, a data set of ocean sea surface temperatures, a data set that I work with in my own research on oceanography. And we were going to load this directly from the NOAA OpenDAP server, which is a remote data access API. But what we realized yesterday is if we're going to have hundreds of people on this tutorial and everyone tries to load this data from the server at the same time, something bad might happen, or we might not be able to get the data. So what we did instead is we moved the data into the cloud. We put it on Google Cloud, and we put it in the Xarray format, and you can load it using the following code in this cell. Okay, and so I'm going to leave this cell up for a long time, and everyone can just run, copy and paste that code. You don't need to know what's happening under the hood here, really, for this to work. This is just going to load up an Xarray data set, and we'll just go from there. If you want to know what's happening under the hood, what's happening is that we're using this package called GCSFS, Google Cloud File System. Google Cloud Storage File System, and we're opening a data set that's stored in the Xarray format from Google Cloud Storage object storage. So it's the same exact data that we would get from NOAA. It's just been mirrored in the cloud to make sure that there's enough bandwidth for everyone to get the data and load it up in their binder or on your laptop or wherever you're running the notebook. If you are running this on your own computer, this should also work for you, but of course I cannot guarantee that you have the package installed on your computer properly and that you have access to Google Cloud Storage. This is public data, so you don't need any credentials to read this. That's what token equals anon mean, anonymous data access. However, you may experience an error. That's why we're recommending people to be loading this data from Binder. So I'm just going to copy this and go back to my blank notebook and paste it and run it for myself. And just leave that up while everyone loads the data. So it loaded for me. I've got a data set here. And I'm going to be doing some plotting in this notebook, even though we haven't formally introduced plotting yet. The reason being, I think it's just kind of boring to have a notebook that doesn't really have any plots in it. So I'm just going to throw a few simple plot statements at you. And I think they're relatively self-explanatory. And just rest assured, we'll go into more detail on plotting in one of the later notebooks. Okay. So I'm going to now just see that we have some data in here. So let's look at this data array. We've got one data variable called SST that stands for sea surface temperature. And if I look at the metadata in here, I can see that there's actually a lot of metadata about what's in here and monthly mean of sea surface temperature and a bunch of other interesting stuff. And I just want to see that I have some data. So I'm going to do ds.sst. I'm going to select the first value in time, and I'm going to plot it. I'm not going to scroll down yet because I assume people are still cutting and pasting or copying the line to load the data. But a plot should have appeared for you. Okay. So I'm going to hope that many of you have the data loaded by now, and I'm going to start moving on. If that is wrong, just make some noise in the chat. So I thought we had Xarray and GCFS in our environment. So those of you who ran it locally, I hope should have these things installed. But I see that there are some challenges. So you can try the other code that's commented out if you like, as an alternative way to load the data. Okay, so what I want to do now is just talk about.
Can you show the alternate code just to be clear?
Yeah, I'll show the alternate code. For example, you can see it on the website where this whole tutorial is up. It would be, I'm not sharing this tab. Okay, the alternate code would be this stuff.
Right? Yeah.
This code that's commented out here. If I uncomment it, how do I uncomment it? Would look like this. Okay, so now I'm going to get into the actual meat of the tutorial. So this is kind of one of the core tutorials for this tutorial, because here we're going to learn how to actually do computations with Xarray. Everything up to this point has kind of just been, okay, load some data, create some data arrays, select a region of interest, but eventually you want to do some actual, you want to put the science in your data science, you want to actually do something. So let's just start doing some very simple arithmetic. First of all, I will remind you that you can get a data array out of your data set by doing something like this. Right? That's a way I can get a data array out of my data set. So I'm going to work with this data array called SST, and I'm going to do various things to it. Okay. So first of all, you may have noticed that this data is in units of Celsius. What if I want it in units of Kelvin? So Xarray actually does have some preliminary support for unit-aware arithmetic, but we're not using any of that here. So we're just going to deal with this as an array of numbers. And if I want the SST in Kelvin, I need to add 273.15 to my SST in Celsius. Okay, so this is the simplest possible computation we could do here, is to just add a constant to a data array. But it reveals a really important property about computations in Xarray, which is that they keep around all the dimensions and coordinates, right? So the workflow that we recommend for working in Xarray is to try to keep all your objects throughout your analysis as Xarray data arrays and data sets, right? So just like this is the same as in Pandas. If you do something, if you add or multiply or do something to these data arrays, you get back another data array, and it has all of the coordinates and dimensions and things like that you had before. We lost our attributes, since we can no longer assume that those attributes are valid for the derived object. Okay, so we can do more complicated things. So let's say we want to calculate some function of some variable. Like the example that we came up with is, say we want 0.5 times NP log of SST oops, Kelvin squared. Okay, so I'm squaring the SST in Kelvin. I'm taking the log of that, and then I'm multiplying that by 0.5. So I get a warning about invalid value in log, but other than that, everything worked just fine. And I got a NumPy array. I got an Xarray data array. So one cool thing we can observe in this line of code is that NumPy functions, most of them kind of just work on Xarray data sets and data arrays. They are applied to those data arrays and return full Xarray objects with coordinates and dimensions. So, if you have some scientific calculation to do, you can do it directly on your Xarray objects this way.
Ryan?
Yep.
Multiple people are asking about preserving attributes while you're doing these operations. So could you demonstrate that?
If you tell me how. I don't know how to preserve attributes. I don't use attributes very heavily, to be honest.
I think you do set options keep underscore attives equals true.
Okay, let's try doing that live. Okay. XR set options. Mm-hmm. The option would be keep ATTRS.
Yep.
Equals true.
Yes.
So Xarray has a bunch of configurable options. And if I run that and rerun this line, for example, I kept the attributes. Wow. We did a live change to the program and it worked. Great. So now that I have that option on, I will just keep all my attributes through these arithmetic operations. Yeah. So it's your choice whether you want to do that. I'm going to kind of call an audible here and skip what's next in the tutorial about applying arbitrary functions. What I was going to talk about there is how if you have a function from another library, other than NumPy, that you want to apply on Xarray functions, Xarray objects in a way that preserves these attributes, coordinates, etc. There's a way to do that. There's a method called apply ufunc that you can call. But I'm going to skip that just based on my reading of the pace, the right pace for this tutorial, and jump to the next topic, which is reductions. I'll make a heading here. Okay. So, reductions are really important. Reduction in Xarray, we're generally working with multi-dimensional data with many different dimensions. There's a lot, and that data can get pretty big. So we almost always want to take the mean or do something with the data to make it smaller. So, for example, we can do SST.mean, and we can do, just as we would in NumPy, we could specify axis equals 0. So this took the mean over the time dimension. Now, maybe we don't remember that axis 0 corresponds to time. That's a piece of information we have to be carrying around in our head that is occupying mental real estate that could instead be used to be thinking about our scientific problem. So instead in Xarray, we can do SST mean dim equals time, which gives us the same thing, but is a lot more readable and a lot less error prone. So we really recommend trying to do these reductions in terms of named dimensions.
Ryan, there seems to be some confusion about the name of the data set. It's now SST, and I guess previously was DS. Could you maybe clarify that quickly?
So SST is the data array. I pulled the SST out of DS, so I said SST equals DS SST, right? I could also take the mean on the, I could apply the same. So here things get a bit complicated. If I tried to call mean on an axis, I guess that kind of worked on the whole data set as well. But I'm just working on the single data array right now. Yeah, SST is a variable inside of the data set. Now, let's do a little exercise. Let's take the exercise is going to be exercise. Calculate the mean over ln and lat. And then bonus, plot the resulting time series. And just work on SST. Okay, so see if you can figure out, without necessarily having been told explicitly, what's the right syntax if you wanted to take the mean of SST over ln and lat. And as for plotting it, it's as simple as tossing a plot command on the end of whatever you calculated. Okay, so I think many of you have probably figured out mean dim equals ln, comma, lat. We can pass it any iterable here, tuple, list, what set, what have you. So now that's just going to give me a time series, a one-dimensional array. And if I just throw a plot on there at the end, I will get this time series of monthly mean sea surface temperature starting in 1960. Just an actual science note here. Anyone notice what kind of trend this data has? It is going up, right? That is not a coincidence. Many of you have probably heard of this little thing called global warming. Turns out, actually, most of that global warming is in the ocean. People have noticed there's some noise in here, and that is precisely the seasonal cycle. So we are looking at raw data from NOAA. I can't believe there is a chat going on in the chat about people believing global warming is not real. The great thing about being a data scientist is you can look at the data yourself, right? So this is real data from the ocean. All right, so let's move on to some more advanced fancy stuff. Those of you who are geoscientists may be noting that we didn't actually quite take this mean in the most right way, because when we're taking an average on the Earth, on the sphere, we have to be aware of the fact that we need to weight the different points differently. So we've got a lat-ln grid here, but there's a whole lot less area associated with the points at high latitude than with the points near the equator because of the geometry, the spherical geometry of the Earth. So we're going to use this as a little motivator to learn some more advanced stuff in Xarray. Okay, so the first thing we might try is to do the weighting ourselves. So let's create a weight array. Okay, so I'm going to tell you that the proper weighting factor for an average on the sphere equals the cosine of the latitude. And we just need to make sure that we're measuring that cosine in that latitude in radians. So this code will create weights. This code will create a weighting factor that is proportional to cosine of latitude. Okay, so now that I've got this weight factor, I can multiply it against my SST. So, for example, I can do SST times weights. And you'll notice when I do that, it kind of just works, right? Even though weights was a just a one-dimensional array, and SST is a three-dimensional. And this is using Xarray's broadcasting capability. So this is another very powerful feature of Xarray, which is that when you are multiplying together two or operating on two different arrays that don't have the same dimensions, Xarray will attempt to align them automatically. So if you've ever worked in NumPy and tried to figure out how to broadcast two NumPy arrays against each other with really this difficult syntax about adding empty dimensions and things like that to make the arrays broadcast against each other, Xarray handles that in a really trivial and straightforward way. So even though this is like a really simple cell of code here that I just showed, it's actually one of the sort of key selling points for using Xarray, that it automatically keeps track of those different dimensions and uses them to align different arrays. Okay. Now, let me give you a naive version of the weighted average. Okay, so I'm going to say SST mean, note that this is wrong, and we'll talk about why it's wrong. SST times weights, sum, dim equals ln lat, divided by the sum of the weights. Oops. I didn't actually import matplotlib. Okay, I'll get this one of these days. What I did here looks like it could be right. You know, I took the thing I wanted to take a weighted mean of, multiplied it by its weights, summed over some dimensions, and then divided by the sum of the weights. So one reason to show this is just to show you some more Xarray code, just to show what it looks like to do things. But this is wrong. This is wrong. We can see just by looking at the numbers that the numbers we ended up with, 2,000 something, are just too big. Those are not reasonable mean values. The basic reason this is wrong is that has to do with how we're normalizing this. One, there's missing data in this array, in the SST, so there's masks where the land is. And two, there are the weights. We have to consider how we're broadcasting the weights. We might actually want to expand the dimensions. So this isn't quite right. So we could dissect all the ways in which this is wrong and try to fix them, or we could use Xarray's fancy weighted averaging or weighted operation capability. So this is something that's relatively new to Xarray and it's really powerful. So I'm going to create a weighted object like this, SST weighted I'm just going to pass these weights. So what this returns is a special type of object called a data array weighted. And I can apply now any type of weighted reduction onto this object. So I'm going to now do SST weighted mean dim equals ln lat plot. And this is the correct global mean sea surface temperature. You can see that it's a little bit warmer than the naive mean that we did before, because it's weighting the low latitudes higher than the high latitudes, as it should be. So this weighted reduction capability is really, really cool. We can do other reductions like standard deviation or sum or median or min max using this object. So Xarray's weighted capabilities are a really powerful way to do computation. Okay, so now we're going to move on to the final sort of big topic for this notebook. This is a long one, but it's an important one, and that is group by. So give me a thumbs up in the chat if you've ever used Pandas group by before. If you've ever used Pandas group by, let me know so I know what sort of familiarity people have here, right? So group by applies a very common modality in data analysis called split, apply, combine. So it looks like people are familiar with this broadly. So group by is very, very useful. And if you haven't seen it before, just follow along and you're about to see a little bit of data analysis magic. So why would we want to use group by? Let me motivate this by just looking at this array at a particular point in space. I'm going to select a particular point in the Pacific Ocean. Lat equals 500, maybe. No, wait, this is the Atlantic. I think this is Atlantic. Yeah. Pretty sure it's the Atlantic. So I'm going to select a specific point, 50 degrees north in the Atlantic somewhere. And what you can see here by plotting this time series is it's totally dominated by the seasonal cycle. Right? So there may be some trends in here, but every winter it gets way colder and every summer it gets way warmer. And so it's really hard to see anything in that data. So in climate data science, we very often remove the seasonal climatology, and group by gives us a really great way to do that. So I'll just show you how that works, right? So the most straightforward way to do this is to create an object I'll call GB equals DS, or so SST, group by, and I'm just going to put here time.month. So what this does for me is create a group by object. And this group by object, we see it has 12 groups with labels 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the months of the year. So there's a lot of different things we can do with this group by object. Basically, we can operate over all of those different groups in batches and do uniform operations on them, right? So one thing we could do if we wanted, we could manually iterate over the groups. So we could do for group name, group data array in GB. And I'll just break out of this iteration right away, and I'll print group name, and I'll show group DA. And this is just showing the first group that corresponds to all the Januaries. And so this data array gives me all the different Januaries from the data set. And if I look at the actual values here, you can actually see in the time dimension, well, that's got all the 1960, January 1st, 1961, January 1st, etc. So generally what we want to do in with group by, so before going on, I see a useful question in here about how did this work? What happened under the hood here? So what happened is that when I called time.month, I'm applying, that's a bit of syntactic sugar that does something a little more complicated. So if we have a time index, as we do on SST, I look at my time variable, can see that this is a date time array. And like pandas, when we have a date time array, we can access different attributes of the time variable using this DT accessor. So if I type sst.time.dt.month, I can get the month out of all of the different time values. I could put year here. I could put day of year here, etc. So when I did SST group by time.month, that is the same as SST group by sst.time.dt.month. Those are identical. Okay, so I hope that answers that question that came up in the chat. Now let's do some stuff with this group. Okay, so the first thing we can do is aggregations. So the way we do aggregations is with a method called map. So we could do gb.map, and we can pass any function to this map. So I can pass a NumPy function like mean. Oh, gb.map. NP mean. So what this does is it calls numpy.mean on every one of those groups and returns me a data array that with all those things that have been rolled into, that have been reduced down to one value. So one value per month. So, okay, so that's okay. So now I have the mean SST for every month, but it's over the whole globe. That's not kind of really what we want. Instead, I would just like to do the mean over the time dimension and still resolve all the spatial patterns. So we can define an arbitrary function that we can pass to map. So for example, I could write a function called time mean that takes an argument and returns the mean over the time dimension. And if I call gb.map time mean, GB, not GP, gb.map time mean, I get a little warning, but instead what I get out is what we would call the climatology. There are 12 months, 89 lats, and 180 lawns in that. So we can write any function and apply it to our group. The thing that we just did is such a common operation. You want to take a mean over some dimensions that it's actually implemented as a method on group by. So we could do that a lot more efficiently by just saying GB mean dim equals time. So I'm going to now assign this to a new data array, this thing I just created. Call this SST monthly mean. And now let's have a look at it. So let's look at that same time, that same spot that we plotted earlier. SST monthly mean, cell ln equals 300, lat equals 50, plot. So now we can just see the seasonal cycle at this location. That's pretty cool. If we want to get a sense of what the seasonal cycle looks like globally, we could do SST monthly mean dim equals ln, plot. And I'll just throw some plotting syntax at you. I'll call x equal month. Let's get 15 levels in there, specify vmin equals -2, vmax equals 30. This is just a preview of what's going to be coming later. So for those of you who like plots, who doesn't, here is what the seasonal cycle in Earth's sea surface temperature looks like as a function of month and latitude. So we can see in the northern hemisphere, it is obviously colder in winter and then gets warmer in summer, what we call winter and summer. In the southern hemisphere, they have summer and winter in opposite phase. So we can see this sort of sinusoidal oscillating pattern. Someone how to extract the evolution of January means of 1 point. That's not quite what we're doing.
There's another question in the chat that asks about the difference between group by and resample. So maybe you could give a general answer.
Resample is next. Although looking at the clock, it seems hard to believe we will get there. So I have to make some choices about what to do.
We can just point people towards resample. That'd be okay too.
Yeah. So I'll show you one more thing related to group by, which is that now that we have this climatology, we can actually do arithmetic on these group by objects. So if I, for example, this is what's called a transformation. Right? So say I wanted now to remove this signal from every point so I could see the evolution of sea surface temperature without the influence of the seasonal cycle. One way to do it is like this. I could define function, remove time mean, and I would say return x minus x mean dim equals time. And then if I wanted to get the anomalous SST, I would do SST group by time month map remove time mean. I'll leave that up there because that's a lot of code. So that's an example of a different type of group by operation. This is what we would call a transformation. It doesn't change the size of the resulting object, but it does something that applies over each group. And there's a quicker way to do this that I'll just quickly show you. If I create this group by object, ds group by time month, I can actually do arithmetic on the group by. So I could do the exact same thing by doing ds anom equals gb minus gb mean dim equals time. So I can do arithmetic on group by objects. So this is a really concise and readable way to do something like remove the mean over a group. And just to prove that this did what we hoped it would do, I will just take that BS enum, SST. I'll select that same point we've been looking at in the North Atlantic. And now we can see that, collapse this a little bit. Now we can see that we have the temporal variability with the monthly mean removed. So we can really capture the long-term interannual variability without all that noise of the seasonal cycle. Now, there's a lot more in this tutorial. Specifically, there's some other functions that work very similar to group by. These are resample, rolling, and coarsen. So just like we applied, I'll quickly show you resample because it's pretty straightforward. So if I want to take the 5-year mean, SST 5-year mean, I can do SST. Let's do BS enum SST resample, and this is again borrowing straight from Pandas and Pandas syntax. I can say time equals 5-year mean dim equals time. I'm just chaining together a bunch of operations now. And I'll just do the same thing, plot the same point. So you can see what that looks like. So what I've done here is I've just resampled the temporal resolution of the data set to be 5-year mean, sometimes called a pentad. So there's a lot more on resample and its cousins, rolling operation and coarsen operation, that are in the notebook, but I think we don't have time for those, and so I think we're gonna just stop here and do another 10-minute break. So thanks to all of you for your patience. We clearly have too much material in our tutorial, and that's a lesson that we are kind of learning on the fly and trying to adapt to. But hopefully you're getting something out of this, and we have a lot of cool stuff coming up if anyone still has any stamina left. So I'll leave my screen up during the break if people want to ask questions. How are we doing on questions here? Okay, I'm going to stop my screen share now. It is about 85 degrees in the room I am in, and I am sweating. This is a lot of work.
It's a lot of talking.
For the next section, is it Deepak who's going to do the presentation?
Yeah, I think I'm doing both now. And so we have an hour left in total, is that right?
Yeah, 1 hour left.
Okay.
Who would you like? And do you want to stay on screen to help, or should I bring Joe or someone else?
Ryan, do you want to break now, or do you want to hang on?
I can go off. I need to eat lunch and take care of my kid.
Just that. Okay. I will invite Joe back on screen then.
Do I have to leave somehow, or are you just going to kick me out?
I'm going to kick you out. It's fine.
I'm going to get some water. I'll be back in 2 minutes.
Okay.
All right. I'm back.
Welcome back, Joe.
All right. Cool. I'll be here.
If you want to turn your camera off, that makes all the icons disappear and makes the screen. Yeah. Awesome. Thank you.
Alex, do we have a attendance count that you can see that I can't?
Yes, there are 140 people right now. It would peaked around, I don't know, 370, 390, something like that, close to 400 people.
Great. It just shows me that there's 1,600 people on Crowdcast, but we can't see.
Yeah. Yeah, I see. I only see for the full channel, not for this particular event. Oh, but I can see a map of where people are, which is pretty cool. People in Chile, people in South Africa, people in Lagos and Nairobi, people in India, people in Thailand, people in Taiwan, people in Korea, people in Japan, people in Russia, people in all over Europe. I'm sorry, I'm not going to name all the countries one by one.
Deepak, I'm looking at your screen right now. I want to make sure that you have a live kernel and it hasn't. You haven't timed out on Binder.
All right, I think I'm back.
You're back. That looks good.
Nice. So Joe, I guess I plans to do the plotting and then the Dask notebook.
I think so. I think we try to aim for something like 30 minutes on each. We're going to have to be a little short on that, but
okay.
So feel free to kind of cut some stuff off the tail if need be, or treat this next notebook as pretty demo oriented.
Yeah. I'll do something like that. We'll figure it out.
Great. So, Brigida, hi. The data that Ryan was using was stored on Google Cloud Storage. It's also available from NOAA on their OpenDAP server. So we're streaming it over the internet. Oh. I don't know what Brigade is asking about.
I think it was the map that Alex was talking about.
Yeah. Okay.
I pasted a map of where people are. It's in the welcome channel on Slack if you want to see it. I don't think I have the raw data, but it's a fun thing to see where all the people are.
Nice. There's one node in the middle of Alaska.
Is that Fairbanks?
I guess.
I think that's Fairbanks. Christopher, the map's in the Slack channel, which I think is going to be the only way we can share it. Hassan, the air temperature data is part of the Xarray tutorial module. And it is loadable using the line that Deepak has up on the screen right now. Can you increase your font size a little bit, Deepak?
Oh yeah, I don't think I'm in. Oh, I am in presentation mode. Does that look better?
That looks good on my end, but we'll have to.
So to Hassan's question, that air temperature data set will be downloaded when you make that call if you don't have it already. There's a question from Richard about downloading from binders. I think you go to File and you click Download, and that should do it.
So, Hassan, the data is stored in a separate GitHub repository. You shouldn't need to use this because Xarray will manage it, manage loading it itself. But it sounds like you're asking where the actual data is stored, so I just shared with you the Xarray data repository. Deepak, will you open the file tab and just show where the download link is there? There you go. So it's on Deepak's screen right now.
Shall we start now? Or?
Yeah, I think we can go.
Okay, I guess we'll start. So this notebook looks at plotting and visualization, and Ryan kind of demonstrated some of this already, which is pretty great. So I just want to start off by saying that to me, this is Xarray's best feature. I mean, everything else is really good, but I make, I don't know, maybe 50 to 100 figures every day. And this was really the feature that got me into Xarray, and also how I got started contributing to Xarray. So my name is Deepak Cherian. I'm also a scientist at the National Center for Atmospheric Research, and this notebook is going to talk about plotting. Our goal here is to, basically at the end of this notebook, you should learn that Xarray wraps matplotlib in a pretty convenient API that uses all of the metadata that we've all been seeing in the previous lectures. And so Xarray's built-in plotting builds on matplotlib, but some of you may be familiar with bokeh and holoviews and that whole ecosystem of JavaScript-based plotting. And so there is an hvplot package that provides similar functionality that's also convenient. But I don't expect that we will get there. So my idea for this notebook really is we'll spend a total of 20 to 25 minutes, and maybe the first 10 to 15 will be more exercise-oriented, while the last 10 minutes will be more about a demo of what you can do, and then you can play around with this later. So first we're just going to do the usual import. So this is matplotlib as MPL, we're getting pyplot as PLT, numpy and Xarray. I'm setting my repr thing, which shouldn't be necessary right now. Really, I'm going to assume that everyone is familiar with matplotlib. And so the data set that we'll be visualizing is this famous air temperature data set. So if you run this cell, it should load some data. And I've done some renaming, I don't remember why, but for now it's going to be called T-air, so it's pretty clear that this is air temperature. I've added a couple of variables, and this is really just for the purpose of demonstration, so don't worry about what's in there. In this case, they look like horizontal gradients, so dt/dx and dt/dy. And this is the data set I have, right? So you see there's 3 dimensions, lat, lon, and time. There are coordinates associated with them, and we'll see that these coordinate values are used when you plot things. And there are 3 different variables, air temperature, and then 2 gradients, dt/dx and dt/dy. Now, I'm going to go here. So the way you use Xarray's plotting infrastructure is to call .plot. And this exercise is basically going to focus only on data arrays, but we have some very minimal data set plotting functionality. And the key point about using .plot is that it uses matplotlib at the backend. So anything you know about matplotlib really just carries over to Xarray, which makes it really convenient. And so let's see. I'm going to type this out. So we have ds, and I'm going to pick this data array. So that's the temperature. And I'm just going to go .plot. And what you get back is a histogram. Is this clear to see? I guess the size is a little smaller than I expected. What we see on top is, at least, you get a nice little histogram, and it's got a nice little label. This 4x daily air temperature. And the way it finds that variable, that name, is it looks in T-air and sees that it has a nice little attribute that's called long_name. And so what Xarray really does is that it uses these kind of metadata. So in this case, the long name and units to create nice little labels. So in this case, you get your X label that's been set by these attributes. Now you'll notice that I didn't actually specify, I didn't tell Xarray explicitly to choose a histogram. The way it does this is through a simple heuristic. It says, if you have a 1-dimensional data array, do a line plot. If it has a 2-dimensional array, it will do a p-color mesh. So this is a matplotlib thing. And then if it's more than 2 dimensions, it will use a histogram. So in this case, T-air has 3 dimensions, so it's used a histogram. Right, so Brett asked a question, so the answer is it looks at the number of dimensions. So in this case, you have 3 dimensions. You can't really do a heat map of that, or it would be quite hard, so you choose to do a histogram. Okay, and so here we have a little exercise. Oops. So again, what we're doing is ds.tr.plot. Is your histogram. So the exercise here is to change this to use 50 bins with unfilled steps instead of filled bars. And so the answer here really is that everything you can use matplotlib. And so if you click this little API thing, oops, I guess I'm not showing the window, but if you click the little API thing, it will take you to the documentation for hist, and you can look up the keyword arguments, and you can pass them to Xarray and basically customize the plot any which way you want. So I'll wait 2 minutes before typing in the answer, so you can all try that out. right, so the answer here looks something like bins equals 50 and his type equals get. And these are all from matplotlib, right? And then you get something that looks like that. So the basic point here is that you can pass these matplotlib keyword arguments down to Xarray and change your plot that way. So anything that you already know really just carries over. So that was for histograms. So now a common question that seems to be coming up is how Xarray is choosing what type of plot it makes. And again, the answer is the number of dimensions. If you look at TL, it's a 3-dimensional variable, so it's more than 2, so that's why it's using a histogram. We can just select one time slice. So again, I've used ICEL, time equals 1. This just pulls the second element along the time axis, or the second slice along the time axis. And so now you see you get a 2-dimensional array. So now this is lat and lon. And now if I call dot plot on that, oops, looks crazy. To see that now I get a p-color mesh plot, right? So now it's found a 2D data array and it's made a 2-dimensional plot. So the really nice thing about this plot is you'll see that the x-axis, for example, goes from 200 to 320. So it's using these coordinate values here in lon, right? On the y-axis, it's using the latitude values. So it's gone from 15 to 75. You'll see that it's done it in the ascending order. It's also added X and Y labels that are, again, based on these attributes. So here you have long name, latitude, units, degrees north, and that's what's being put on the Y-axis. And similarly in the X-axis, it's also added a nice color bar, and it's, again, added this nice label that says 4x daily air temperature with the unit degree Kelvin. And in addition, the title of the plot says time, gives you the timestamp that you selected when you made this figure. So there's a lot of information that Xarray has added, right, to what would be a normal matplotlib plot. Now in this case, Xarray has chosen the p-color mesh, but this is configurable. So the way you would do that is you cell time equals 1, plot, and let's say we can do a contour plot. And now you get a contour plot. And you'll see that it's done the same thing, where it set axes using the coordinate labels, and it set nice names for your X labels and Y labels, again, choosing from the attributes of the data array. There aren't many questions, so I'm assuming that people are following along. And so, this is the most basic figure, and there is a lot of options that we've added. And so here there is a link to all the nice options that we support. I'm going to type this out just as a demonstration of all the common things I tend to do. So again, I'm going to pick. So I picked a 2D array. Then I'm going to do plot. And so let's say I really, usually what I do is, for example, maybe the dynamic range in this color map is not so good. So I use robust equals true. And what this does is uses the second and 90th percentile of the data to set color bar. Oops, for the limits. So if you do that, you'll see now you get this nice color bar that's got the little triangles at the edges, and you can maybe see a little more detail in everything that's happening. So this is one nice thing. You can also customize the color bar, for example. That works by doing things like this. There's a little C bar under quads. It takes a dictionary. And you could do my label. You can move the color bar to the bottom of the screen. You can do aspect ratios. The real key point here is these are all matplotlib things, right? So you can do this. The real key point is that these are all matplotlib quarks. And so this is really just passed on to plp.colorbar. So again, you can take anything that you know and all the customizations that you like to do and apply them on your own. Blaine has a question about specifying the labels rather than default values. So our recommendation is really just to use matplotlib. So you would do something like plp.gca, gets you the right axis, and then you do x label, let's call it new x, and let's set y label new y, and that. So this is our general recommended pattern, is that you can use Xarray to kind of get your initial plot really conveniently, and then you can use matplotlib to make all the complicated changes you want to. One feature that I forgot to add is that you can add things like x equals latitude, for example, and then totally flip the plot. Oops. I need to set x equals lat. So now you've flipped it, you've actually put latitude on the x-axis and longitude on the y-axis. So that's, I find, a really convenient feature. Okay, let's see. So I think I'm going pretty slow, so we'll have to do this a little quickly. One of the exercises here is to update the above plot to use a different color map. Again, this is using matplotlib, as I keep saying. So you can just use cmap equals, I'm going to pick red, yellow, blue, and bam, now it uses red, yellow, blue. And so there are a lot of these keyword arguments that you can look up. The point is that we wrap a lot of matplotlib functionality, so if you know how to do something with matplotlib, you can do it, including, yes, you can also set jet. We let you do what you want. Anyway, so the point of Xarray is to just let you do little convenient things with your little metadata. So things like axis names and coordinate labels get set automatically. And things like x labels, y labels, colorbar labels also all get set automatically, right? So in this case, I set latitude on the x-axis and it's put the right label there. Again, just I'm going to skip this exercise. So it says overlay a contour plot. So this, again, you just add a second call to dot contour and it will plot it on top because, again, things are working like matplotlib. So one cool thing then, now we've looked at three-dimensional arrays and it uses .hist. And with 2D arrays, it uses p-color mesh. And with 1D arrays, it basically does a line plot. And again, here you'll see, let me do this again. So I've used ICEL to basically pick out just now a section along latitude. And we call that plot, and we'll give you a nice line plot. And again, as usual, you can pass keyword arguments down to matplotlib, and so you can do things like that. One really nice feature is that sometimes you may want to have, I want to see 3 lines along 3 different latitudes, right? So let's see how we would do that. I'm going to select time equals 1, lon equals 10 again, and lon equals 10, 20, and 30. Now this is a 2-dimensional array, but let's say I wanted 3 lines along lon. The way we can do that is to say hue. And I think this syntax is copied from Seaborn, actually. So if you're familiar with that, this should be familiar. And you could do y equals lat, because I'm used to looking at latitude on the y-axis, and you'll get something like this. So the y-axis is latitude, the x-axis has a temperature. Again, they have nice labels. But now you have 3 lines, 1 for each longitude, and we've also added a nice little legend that gives you the dimensional value. So this is longitude equals 225, 250, 275. All right, and so we've kind of covered this already, and we're kind of running out of time. So in general, the general strategy for making plots that are more complicated is you could create a matplotlib axis. You can use Xarray for its convenience, and you get something like a close approximation. And then you can use matplotlib to just customize it as much as you want. And this is generally how I make publishable figures, for example. But now I'm going to skip on to this idea of facetting, because that to me is really cool. So here I'm going to do basically what Ryan demonstrated, which is I make a bunch of monthly means. So in this case, I've got a bunch of monthly means. So I have latitude, longitude, and there's 12 months. So I have that. And so the idea is basically now we have these monthly means of air temperature, and I want to see all of them, all 12 months on a single figure, right? The way this works is using something called a facet grid. The way you access that functionality really is to just specify row or column, right? So in this case, I have monthly means, got TAir, and is a three-dimensional variable. I'm going to call that plot. I'm going to say along each column, I want a bunch of months, but I want no more than, actually, let's just do this. So you get that, all right? So you see it creates a bunch of subplots. It's created 12. It's added the titles, month equals 1, 2, 3, 4. So you know what they are. It's added a color bar, and you've got X and Y axis labels. But this is kind of not so useful because 12 is too tiny. So you can tell it to say, I want a maximum of 4 columns using this call wrap. And it should work. There you go. And so you get something like that. Yeah, I agree with Denny. That is awesome. And I do this frequently. So now you get this nice 4x3 grid where each panel shows a different month, and you can kind of see things changing with months, right? Again, the interest of time, this is now becoming just a demonstration notebook. But so you can do this literally by just filling out a column, right? And so here's a different call. So again, it's got call equals month, call wrap is 4. That's the same call as earlier, but now I've added all these things we had earlier. So things like robust to set limits. You can set a color bar. You can choose to put your color bar at the bottom. I'm just going to run it. And bam. So everything that, all your customizations are basically possible. And it makes it really convenient to visualize your multi-dimensional data, which is really what Xarray is all about. All right. So now, the other cool thing that happens here is you'll see I have assigned this function plot is returning this thing FG, which is called a facet grid object. So let's look at it. And I've linked to the doc string, but basically this grid, this object provides you a bunch of useful attributes. So there's .fig, there's .axes, and there's X labels and sets Y labels. So your exercise now actually is to, let's just take, this thing makes a nice little facet grid plot that we saw in the beginning. And your goal now, or the exercise, is to set a title for this figure. Sorry, I should put this down below. Okay, so I'm back here in the exercise thing. Okay, so your exercise is you add your code here, and it should use the figure that's subtitled to set a title for this figure, right? Looking at a few questions. Okay, so I'm going to take 2 minutes to answer some questions, and you guys can work on this. Question is, could you put them together in a nice animation? I think you have to do this manually right now. So either use matplotlib somehow, or I usually just save 2 PNG files and then animate with FFmpeg. Is it using gridspec under the hood? Yes, it is. It actually calls plt.subplots. So you can actually customize it that way. So in the interest of time, I'm just going to do this. So the answer is you have fg.fig is a matplotlib figure. So I think this will just work. And so you'll see it's added, this is my super title, right? So again, this is just underscoring the point that this is all matplotlib under the hood, which is a great library. And so it makes life easy. And you could also things like changing those labels, etc., etc. It's been close to 20 minutes. So the rest of this notebook is going to be kind of a demonstration thing. And then you guys can play with this offline things out. Here, again, this section is on facetting. So I'm making my facet plot, and it illustrates two methods. This is called map data array, and just a general map. It's easy to explain, and you see what the output looks like. So in this case, we have a p-color mesh in the background. We have some contours. So the contours were added using this map data array. So you add contours of the same data that was in the initial plot. And it's basically an Xarray plotting function, but again, under the hood, it's matplotlib. And I've added this little white point on every panel. And so an easy way to do this is to use fg.map. So not only can you easily make these kinds of plots, but you can kind of pretty conveniently modify them. Again, customize them as much as you want. And so I would encourage you to look up the documentation, and you'll see a lot of cool things. This is a cool example that I'm going to skip and instead switch over to geographic plots and CartoPy. Again, the general pattern here is you create your matplotlib thing, you call Xarray for convenience, and then you use your matplotlib stuff to customize your plot. So here, I'm creating a little axis with a projection. So this is how you would usually create a CartoPy axis. And then this is our usual plotting. But in this case, I specify axis, which is plot to this particular axis. And I do the transform equals plat Xarray. So this is important. And again, usual CartoPy thing. Bam, right? So now you'll get this nice little projection. You've got your data on that. It's still got the nice labels on top and the bottom. And here I've called a CartoPy function to add little coastlines, right? So again, I can't emphasize this enough. Like, this is all just CartoPy and matplotlib. Xarray just offers you a very convenient way to get started with things. And then you can kind of make it as complicated as you want to. You can also literally take the same approach and facet with CartoPy too. So you can do things like this, which is common for my work. And so many other things are possible, right? So in this case, I've used the map feature to plot coastlines on each of those axes, right? So in the previous example, I used it to add a point, and here I'm adding coastlines. And so now, hopefully that was a quick tour of what you can do, and you can play around with it. For the last kind of 2 minutes, I would quickly just demonstrate hvplot. So up till now, we've just looked at matplotlib. There's a whole other, there are multiple other plotting ecosystems, but one of them is HoloViews, which builds on Bokeh. And so there are little links that you can use to see what these are, but it's easy to demonstrate. So you basically run one line, which seems to be taking a while, okay. And then you call instead of .plot, you call .hvplot. And you see it gives you a nice little histogram. It's interactive. So you can do things like this and look at the values. You can zoom in, zoom out. You can do that, all kinds of things. It's great. And it's basically just as easy as using .plot. You can get your little 2D plot now. So again, it makes the same decisions that Xarray does. So you get a histogram, you can get a 2D plot, you can get a line plot, and again, you can check all your values, which is really cool. This I really like. So here's where you plot a little argument called group by on time. And so in this case, I've given it a full 3-dimensional array. And what it does with this group by is create this nice little slider. So you can do This is taking a while to load. I swear this worked yesterday. Yeah, I guess something has broken. Anyways, we will look into this, but for now, I just wanted to point out that you have .plot to access a whole bunch of Matplotlib functionality, and you can install hvplot and you get a similar .hvplot. And similar command gets you an interactive graph. You could probably do the same thing by changing a Matplotlib backend too. So it's really just what you prefer and what you want to do. Yeah, so some people have it working in Binder, which is great. This should be working. So I think I'm just going to stop there and maybe take a 5-minute break before doing the Dask lecture. So thanks.
Great. So we'll start again at 40 minutes past the hour, and we'll do the last 20 minutes on Dask and Xarray. So this will be.
Do you have any suggestions? Sorry.
Oh, yeah. I was going to say this is going to be Notebook 6, and we will do our best to get as much of that material in as we can in 20 minutes.
So what do you think, though? Should this last one just be kind of demonstration? It gets pretty advanced at the end.
Yeah, I think let's just get through the beginning part and see how that goes.
Okay.
I can explain why we're skipping Notebook 5 once everybody comes back.
Yeah, sounds good.
So just give me a minute on that, and then you can take over on Notebook 6.
Sounds good. Yeah, so there's a question why the animations didn't work, and I really don't know. I tried it out yesterday, and it was working in Binder. Do you have any thoughts, Joe?
No, it's possible that no, I don't have any specific thoughts. I'm guessing that because we've had Binder running for a while, that something's come disconnected.
Yeah.
But I don't have, I don't know.
So there's a question about exporting animated HV plots. So I have never actually found the answer to this. Do you know?
No, I don't. I do believe it's possible, and we'd have to look. I would Google it.
Yeah.
Wonder.
Animations didn't run locally. Interesting.
It's possible that we're missing the PyViz Jupyter Lab extension, but it seems to be working for some people, and I don't know why that would be. But
yeah, it seems to have bokeh and stuff installed, so
yeah.
No idea. Oh, we made the PyViz extension. I've run into this issue before.
Yeah.
All right, well, thanks for the feedback, guys. We'll figure this out for the next version.
All right, we're going to get started here in about 30 seconds. Deepak, will you switch to the notebook 5 just for a moment?
Yeah.
You can just leave it here. It's fine. All right. So, great. Welcome back, everyone. We're going to get going with the last 20 minutes of the tutorial. We were planning on running everyone through this notebook that's up on Deepak's screen right now, which is the Intro to Dask. I'm hoping some of you that are particularly interested in Dask managed to make it to the Dask tutorial earlier this week. And I want to just stress that there's a lot of information there in that tutorial and that it's a really good resource. And so you can look into that. We're going to mostly skip this introduction to Dask, which this notebook doesn't have any Xarray pieces in it. And just tell you that this notebook is here in the repository for you to look through in some self-guided time. And that the key point is that Dask is a library for parallel computing that enables us to do chunked parallel data processing of multidimensional arrays. And so Deepak's going to show you the notebook on Xarray and Dask. And the main thing to remember here is that we're going to mostly substitute NumPy and NumPy arrays for Dask arrays, and that they have a similar enough API that Xarray can treat them in a very similar fashion. And we can do a lot of the same things we can do with NumPy arrays and Xarray as we can with Dask arrays. So that was the entire Intro to Dask section of the tutorial that we're kind of cutting down in the interest of time. And feel free to read through it. And I'm happy to answer some questions in the chat as Deepak gets started on the Xarray and Dask notebook.
Right. So we don't really have much time. So this is going to be kind of a quick, again, more demo-like, but you guys can work with these notebooks on your own and learn some things. So again, one of Xarray's other superpowers is that it integrates with Dask pretty seamlessly. And so the goals of this notebook are you learn that Xarray objects are really also Dask collections, which means you can basically pass them to little Dask functions and things will do what you expect them to do. All of Xarray's built-in operations like mean, et cetera, can transparently use Dask. So that makes it really convenient. And we also provide at least 2 functions that make it easy for you to use Dask to parallelize your custom functions on Xarray objects. So we're going to start by doing some imports. So this is NumPy as MP, Xarray as XR. And then you're going to use this Dask distributed. So this bit is basically how you set up Dask, right? So it's totally independent of Xarray. And if you run this, you should be able, if you are in Jupyter Lab, you should be able to see this little Dask dashboard icon. If you click it, it will give you a bunch of things that you can click on. So by default, you should see the progress and task stream. You can add other things. For example, Dask workers. In this case, we have 2 of them. So anyway, there's a lot you could look into there. But this dashboard basically provides you a way to monitor your Tableau computations. So if you're running locally and don't have the dashboard, you can also click on this link. And it should take you to a page that looks pretty similar. And so we'll just check that this is working. So you'll see that a bunch of tasks came up and it's computing through them. So it ran 2000. In this case, I just asked it to create a bunch of ones and it's running. So this is really just to exercise the dashboard and make sure that everyone's on the same page. So if you could see that when you ran the cell, can you type +1 into the chat? Oops. Okay, it seems to work with some people. You should basically just work on binder, and locally you may have some issues. So if you're running locally, you should be able to click this little link. And if you're seeing a notebook interface, you need to add /lab at the end at the top and remove the tree. Okay, enough people seem to have it that I think I'm just going to go ahead. This bit is going to be a little quick. So we've been loading up this air temperature dataset, and that's been coming back as kind of Numpy arrays. What we're going to do is specify the chunks attribute. Sorry, I think I've lost a cell. Okay, so before we get there, let's think about how Dask works. And the way it works is it takes your huge Numpy array and it cuts it up into little blocks. And so in this case, let's see, I'm going to just, on this, in this case, we have 25 by 53 by 2920. And this is basically a decent sized array. And I'm going to make this a Dask array by saying I'm going to create chunks or cut this array up into little pieces where there's 10 along latitude, and along longitude, and maybe 1,000 in time. Let's look at it now. If you compare these two wrappers here, you see it says, just a ... but here it says a Dask array. And then if you click this little database thingy, you'll see that a wrapper for Dask, right? So this says you have an array, each chunk or each block of the array is 400 KB or whatever. And so the way to visualize this is to look at this little figure. So you can see that this big cuboid is your whole data set. And within it, you'll see some little divisions. So each of those kind of sub-cuboids is a block of your data set. And it's basically size so that there's 10 chunks in lat, 10 chunks in long, and then 1,000 in time, right? So you've cut this up into little smaller pieces, and all of your operations will now work on the smaller pieces. That's how Dask works by parallelization, right? So it has a bunch of workers. You could have, if you're running locally, it's basically equals the number of threads you can run. And so you will take all these little pieces of the array and send them out to all your workers and do whatever computations in parallel, and then bring back all the answers. So we've seen the wrapper for air, so there's a little Dasky thing, right? And so here's the cool bit. So here's a mean statement, so it's .mean time. You notice that nothing happened on the dashboard. And if you look at the row for mean, you see you got another Dask array back. So Xarray's built-in operations try very hard to just keep Dask arrays as Dask arrays, right? What this means is you don't actually load all your data or do any computes or get any real values until you explicitly ask it to, right? So you start with a Dask array, you call mean a long time. Now you get a data array, again, it's an Xarray thing. because you've reduced it, where you get a data array that wraps a Dask array. You can do it with selection, for example. So again, here's an ICEL call. It's just picking out a time series at this particular point, and again, you get a Dask array. So all of these operations are quite cheap and quick. And you can do this with, resample, coursing, everything that you've seen so far. Yeah, something's wrong with this notebook. Anyway, so here's kind of a rolling example that we haven't seen, but you can kind of do all kinds of complicated things. What's going on? And so at this point, you just have a Dask array, right? You don't actually have a value. And so the way you actually get a real value from this is to call .compute. And so I do that, and you should see some activity. Whoop, that was maybe too quick. We seem to have lost the connection to the little thing. It's not really updating here. But anyway, so now you'll see that you get real values. So this thing is a NumPy array, right? So this is a wrapper for a NumPy array with a bunch of values. And so just to really demonstrate this fact, here's the wrapper for mean, and it says you have a Dask array. And here, and you don't actually have any values so far. You just have this representation of a mean. And when you call .compute, you get actually concrete values back, right? So this has done its computation in parallel and brought all the values back. And so again, just emphasizing, mean still has a Dask array, but when you call .compute, you get back real values. Xarray has a little convenience function called load. And so when you call load, it actually replaces your Dask array with the real value. So it will call compute, but then do an in-place replace. So if you look at mean again, now you see it's still got these values. So this is just a convenient shortcut. It's just a convenient shortcut for calling .compute. I'm going to skip that bit. So this one is a little important. So we know we have ds.air, and then when you look at the wrapper, again, you're seeing a Dask array. But how do you get that Dask array out of an Xarray thing, right? Sometimes you may want to do that. So the answer is we hit .data, and now this just gives you a Dask thing. So you've lost all the Xarray stuff, right? So you've got the underlying data structure. And so in general, this will just give you the underlying data structures. In this case, you got a Dask array. If you did it with mean, so mean, for example, has a NumPy array. And so if you do mean.data, you'll get a NumPy array back, right? So this is, if you want to go one layer down. Tiago asks, is the mean operation distributed or only the data? The mean operation is distributed. So it's computing in parallel and then bringing back the final answer. You should be able to see it on this dashboard if it did work. But yes, so all the computations are distributed. So that's .beta. There is another property called .values. And so again, if I'm looking at ds.air, it has a Dask array. But if I call .values, you will always get a NumPy array back. So this ends up called compute. But you should be able to see, but you don't see for some reason, unfortunately. So the kind of quick summary so far is that Xarray is kind of a high-level wrapper for these underlying objects. So far, we've seen NumPy arrays being wrapped, but Xarray can also wrap Dask arrays, which means you can seamlessly parallelize your operations. And then these .data and .values are a way you can get to the underlying data if you need it. Okay, so I'm going to scroll down. Right, so we didn't do our Dask orientation. So how is Dask working? Right, so here's my, let's just look at mean. Mean in this case was loaded. So let's see, we'll do ds.add the mean time. And I'm going to just change this on the fly here, just so that we can get a nice figure. notebooks. Okay, I apologize. I seem to have chosen not very optimal values. Okay, we have this mean. The mean's a Dask-backed Xarray, right? So there's a Dask array there, and then I can pass it to Dask visualize, and this will show you a big graph. And so basically, each circle, which is maybe a little hard to see, is a little task that Dask will execute in parallel. So all of these tasks are what go into computing the mean. All of those tasks get sent out to the workers. So this comes to Thiago's question about the mean being distributed. And so it does all that, and then it sends the values back, and you get back an Xarray, right? The key point is Xarray things like mean here can be passed to Dask functions, and so that's a really convenient interface. Again, if you knew Matplotlib, you could understand Xarray plotting. If you know something about Dask, you can also understand how Xarray objects behave, right? And so fundamentally, our goals for this were to show you that Xarray can pretty easily wrap Dask, and it does it pretty seamlessly. All of Xarray's built-in functions will know how to use Dask and will all operate in a distributed fashion. So this includes resample, group by, coursing, rolling, all kinds of complicated things. And even the usual reductions like mean, as we've just seen. So this makes it really easy for you to parallelize your analysis, even just on a local, 4-core laptop. It will get a pretty nice speed up. And so we have only 5 minutes left. So I think I'm going to stop there and just point you to this section, which is automatic parallelization. And the use case for this kind of thing is, we have implemented things like mean and variance and things like that, but sometimes maybe you want to apply something in SciPy, and SciPy functions don't know how to deal with Dask, and so you have a few options for dealing with that use case. When you have time, and if you're interested, and if this is something that you need, I would encourage you to look through this section to figure out all the different ways that you could parallelize those functions on Xarray objects. So yeah, I think we'll stop there. Maybe take the last few questions, but thanks for listening.
Any questions on Dask or the final couple sections here? I'll remind people that the introduction overview notebook 00 has 4 examples that all use Xarray and Dask on larger scale problems. So you may want to run through those as kind of self-guided example notebooks. Great. We're getting lots of thanks. Not very many questions. Yeah. That's good. You nailed it, Deepak.
Thanks. I think we all did pretty well, given the amount of material.
Lessons learned.
Does Xarray integrate with Databricks koalas? No, I guess. What can be a potential example of how to get involved into Xarray as a contributor? We have a bunch of issues on our GitHub tracker, marked good first issues. I got involved with the plotting thing just because that's what I was doing and it would make my life easier. I think we all have our individual stories. But we're pretty welcoming. We'd be really happy if you started participating, even just by answering issues or sending in PRs. You could also please help with updating these tutorials or documentation as you learn new things.
There's a question here for someone's asking just for a link for some examples around using map blocks and apply ufunc, and I'm going to paste that in right here. Just a second, automatic parallelization.
I have to say, I think with that next release, which should happen in the next few days, there will be pretty decent map blocks documentation.
Yeah, most of this right now is apply ufunc, which is its predecessor. Yeah, so Chonwan, I just put a link in for some additional documentation on the automatic parallelization. Okay.
The latest version of our docs, there's a little more text on that stuff too, if anyone is interested.
All right, we're almost on time here. Alex here.
Yeah.
I will export the chat, and I think I'll just paste it in the Slack channel for now. If you want to save it somewhere with the data for the tutorial, just go ahead.
Okay.
If you want to continue the discussion, the tutorial Xarray channel, I'm pasting the link here, is the best place to go. And that's all I have to say. Do you have closing words?
I just thank you everyone for coming and for bearing with us as we kind of calibrate the 4-hour remote tutorial experience with this content.
Yeah, thanks for being encouraging on the chats too. That's pretty helpful.
All right, thanks everyone. Have a good morning, afternoon, night, and
thanks,
enjoy the
Alex.
rest of SciPy this afternoon. Sorry. Yeah, you're welcome.
Thanks, Alex, for moderating. That's great.
You did all the hard work. I was just marking questions as answered.
All right. Well, bye.
Everyone.
We'll see you around.